Okay, so let's take a look at hypothesis testing when our hypothesis is about a distribution. And what do I mean by that? Let's take a look at an example. So now we're going to look at another jury selection problem. So we saw the Swain case in Alabama in 1965. Now we're going to take a look at Alameda County in California, up where Oakland is, in 2010. And the question will be the same. Are there racial biases in the selection of juries in Alameda County in the year 2010? So to give some context, remember how juries are selected. So you start with the eligible jurors in a county, and then you further reduce this to the eligible residents, so people who are registered voters, for example. And then you further reduce this to a jury panel, and then you take this jury panel and you reduce it to a jury. And California law says that the way that people should be selected for jury service should result in a representative sample. So they even use the word random, should be selected at random from a source representative of the population. So in the year 2009-2010, the ACLU took a look at this and kind of concluded that this isn't what's happening in Alameda County. So what they did is they took a look at 11 felony trials in Alameda County in the year 2009 and 2010. Between those 11 trials, that was roughly 1,400 people who reported for jury duty. And so they took a look at the racial breakdown of those 1,400 people, and they recorded them here. So they put people into 5 categories, 5 racial categories, and they counted the proportion of each. So they saw that 26% of the jurors who reported for jury duty were Asian, 8% were Black, 8% Latino, 54% white, and 4% identified as another race. They compared this to the demographics of Alameda County at large, which is 15% Asian, 18% Black, 12% Latino, 54% white, and 1% of people are from another race. And so they saw that, these numbers look somewhat different. They said that the difference was somewhat large. So in this case, Asian people were overrepresented in the jury panels, Black people and Latino people were underrepresented, and so forth. And so the question is, we have 2 distributions here. We have the distribution in the population, and we have the distribution in the jury panel. Are these two distributions significantly different from one another? We can answer this question using our simulation skills that we've learned over the past couple of lectures, but to do that, we need some way of measuring how different this is from this. So to hammer that home, what we're trying to figure out here is whether or not these differences, this distance, is meaningful. Is it significantly different? So we'll come up with a model. Our model will be that the people on the jury panels were randomly selected from the eligible population. The alternative viewpoint is no, they weren't. There was some bias here. They weren't randomly selected. What we observe here is an empirical distribution. It's this. Okay, this is what the ACLU went out and measured. And the question is, how different is it from the proportions in the population? So the question is, how do we measure that difference? We need a statistic here, okay? A number that quantifies that difference. And that's what we'll talk about here in a second. Oh, need to define my jury panel. Okay, so we put all this in a table here. See, what we have here, what we're visualizing here are the 2 distributions. So we have the eligible jurors. This is the population. Those are the blue bars. Okay, and then we have the jurors who actually were selected for the jury panel and who appeared in the jury panel. And those are the red bars. So now you can see that that Asian people are overrepresented, Latino and Black people are underrepresented, and so forth. The question is, between these 2 distributions, the red distribution and blue distribution, how different are they? So to quantify the difference between the 2 distributions, we're going to come up with a new statistic. Okay, so what we have here is a categorical distribution. Okay, so we have basically several categories, and then we have the percentage of people who fall into each category. And then what we want to do is we want to measure the distance between two categorical distributions, or if you want to think of it this way, the difference between two histograms, if you'd like, or the distance between two bar charts. And so here's our idea. It's called the total variation distance. Okay, this is a standard way of calculating the distance between two distributions. Basically what you do is you take a look at each of the bars. Let's go back to this picture here. Okay, so you look at each pair of bars, right, because the distributions are aligned with one another. Okay, and you say, okay, take a look at this difference here. Okay, that's 3% if I remember correctly. And you take the absolute value of that. You take the difference here, that's 0. You take this difference, and that difference. You take all of their absolute values, you add them all up, and then you divide by 2. Okay, so that's what we're doing here. We calculate the differences here. Okay, so I'm going to take the proportions in the jury panel minus the eligible. Okay. Those are the sign differences. What we want are the absolute differences. So I'm going to take the absolute value of that. Here's what I get. Okay, so I have the difference here. That's signed. I don't really want the sign, so I take the absolute value. Okay, so I have all of the absolute values. I'm going to add all of those up and then divide by 2. That is what we call the total variation difference, or the total variation distance. Okay, so here we see it's 0.14. Okay, we'll talk a little bit more about that in a second, but I just want to note that if these two distributions are exactly the same, what you're going to get is 0, right? Because if they're exactly the same, the difference here will be nothing. There will be no difference here, no difference here, here, or here. And you'll add up a bunch of zeros and you'll get 0. So the larger this number is, the more difference there is between the two distributions. The question is, I got this number back, 0.14. Is that a big distance? Is that a small distance? We don't really know. We have to put it in relation to something. And the way we do that, again, is with simulation. Okay, so first let's make a function which calculates the total variation distance. It's going to take in 2 empirical distributions, or 2 columns of our table, if we want to think of it that way. It will return the TVD. Okay, so then we're going to test it out here. We're going to apply it to our eligible jury distribution, and then our distribution actually in the panel. We see that it's 0.14, as we saw before. So the question is this a large number? Okay, so how do we determine if it's a large number? So what we're going to do is we're going to start with the assumption that the jury panels are selected at random from the population, the overall population. In other words, we'll start with the assumption that everything's fair. Okay. Then we simulate drawing a jury panel. It's going to be different. It's not going to be exactly, it's not going to follow these proportions exactly, right? It's not going to be like, oh, we see 15 Asian people, 18 black people. There's going to be some difference. We measure that difference and we see how large that TVD is, that total variation distance. And then we see how often is it that we see something as large as 0.14. Okay, so let's try this. We're going to get our distribution of eligible jurors, and we're going to put that into our NumPy random multinomial function. So remember, what this does is you say, okay, I want to select this many jurors, and here are the probabilities for each category. So I'll run this. I'll take a look at sample distribution here. I'm dividing by 1453 because remember, the result of NumPy random multinomial is the number of people. And so I divide by 1453 to get the proportions. Okay. So I selected a jury, then I have, this is the percentage of people who were Asian, percentage of people who were black, percentage of Latinos, percentage of white people, and percentage of people from another race. And so I do this over and over again, I get different breakdowns. But they all look pretty similar to the overall population breakdowns, okay, if you notice. Okay, so I'm just going to take this, I'm going to take the result and assign it back to a table here. And remember, what I'm trying to do is do this over and over and over again and take the difference between my random sample, okay, and the eligible population. Because what I'm trying to figure out is what is a typical TVD distance between a sample and the population. Okay, I can take a look at my bar chart here just to kind of get an idea of what's going to happen. The yellow bar is the random sample. Okay, so the blue and red bars are as they were before. The blue is the population. The red is what I saw actually in this jury panel. In these jury panels, the ACLU study. And the yellow bars are a random sample. And what we tend to see here is that the yellow bars are very close to the blue bars, meaning that whenever I take a random sample, it looks pretty much like the overall population. Okay, so let's calculate the TVD between our random sample and the overall population. We see it's 0.01. Okay, compare that to 0.14, which is what we saw whenever we selected the TVD between the ACLU study and the overall population. So this looks quite a bit smaller. 0.14 in comparison looks quite a bit larger. But in order to get a better idea, what we're going to do is simulate this over and over again and see how rare it is to see something like 0.14. Okay, so we're going to put together a simulation just like we've been doing. We're going to run 10,000 trials here. And what we're going to do on each trial is we're going to select a jury panel from the eligible population, calculate the TVD between our selected jury and the population, and then append that result to an array. So we ran the simulation. Let's take a look at the results. Okay, so here are all of the total variation distances that we saw. 0.02, 0.01, 0.02. They're all like 0.02 or smaller. Like 0.03 seems to be the upper bound here. So what we're going to do is we're going to visualize that distribution. Here are the TVDs we saw. Okay, so the most frequent, or kind of like the mode of this distribution, is a little less than 0.02. Okay, and we very rarely saw a jury panel with a total variation distance of 0.04. Okay, so these are the typical distances. If I randomly select juries, this is how different they are from the overall population. It's a way of quantifying how different the jury panel is. And so if the claim is that, hey, the ACLU, yeah, you saw some differences, but it's just due to chance, we can actually measure the probability of seeing something that extreme. And in this case, I measure the probability of seeing something as far away as 0.14 from the population, and I never see it. My estimated probability here is 0. So I use that to conclude that the jury panels are likely not representative. So the panels that we saw from the ACLU study are not like the panels that we would get from just randomly sampling the population. So again, we conclude that there must be some bias here in the process. And at that point, we have to stop because we can't say much more. Okay, we say that the distributions are different, there's something going on, and we have to investigate. So in the case of Alameda County, there were several sort of suggestions that were put forth. One is that the juries are drawn from voter rolls and from vehicular registration, and those might not be representative of the overall population. So in that case, they were randomly selecting from something they thought was representative, but which wasn't actually representative. So that was still against the law because they weren't representing the overall population. So a summary of what we've done here is that whenever I'm trying to see if one distribution is like another distribution, what I want to measure is, I want to have some way of quantifying the distance between two distributions. And the way we do that, one way of doing that, is with the total variation distance. It measures the distance between categorical distributions. So what I did to figure out if the TVD that I saw was actually, large or small, is I ran a simulation a bunch of times, sampling from the population, getting a bunch of TVDs from those random samples, and seeing how large was my empirical TVD to the actual TVD.